Hello, welcome. I'm Kylie from Syracuse University. I'm very happy to talk about our paper, Cost-Effective Data Feeds to Blockchains via Workload-Adaptive Data Replication. This is a joint work with my advisor, Professor Yu Tang, my colleagues Jiaqi, Zhehu, Chen, and Professor Jianliang Xu. First, let me introduce some background of our work. What is data feed? Data feed is a DF designed paradigm to feed external data to Ethereum like blockchains. It is widely adopted in decentralized finance. There are two popular examples. A stablecoin like DAI, which needs to read the real-time Ether price feed. A Bitcoin-packed token like TBTC, which needs to read the newly found Bitcoin blocks and use a sidechain feed like BTC Relay. This list shows the top DFs that pays so much for the use of data feeds. They pay millions of US dollars every month. So the goal of our work is to optimize the cost of data feed. Existing data feed adopt static design where data is either pushed or pulled onto the blockchain. We collected a real DeFi workload and we found that the access to the data feed fluctuates over time. As the finger shows, the number of reads after a write varies a lot. Therefore, we focus on dynamic workload-aware cost optimization. To better motivate our work, let's look at the two baselines of data feeding. In the push-based feeding, there is an off-chain data producer that pushes every data updates onto blockchain. That means there is always a replica on-chain. In the pull-based feeding, the off-chain data producer stores the data updates off-chain, and the data feed is pulled on-chain on demand. Ethereum charges users when executing smart contracts. In the cost model, a storage write charges user 20,000 gas, and the sending a transaction costs 21,000 gas plus 2,000 more gas per word. By contrast, a hash is much cheaper. In the baseline 1, the writes are sold off-chain and the reads are sold by sending a transaction to load the data from off-chain to on-chain. In baseline 2, the writes are always replicated into blockchain and the reads are sold on-chain. In baseline 1, the reads are very expensive because of sending a transaction. In baseline 2, the writes are very expensive because of the expensive storage rights. And we did a preliminary measurement to show the trade-off between the two baselines. In the finger on the left-hand side, the workload is rate-intensive, and we can see that baseline 1 is much cheaper than baseline 2. On the right-hand side, the workload becomes rate-intensive, then baseline 2 is much cheaper than baseline 1. So the lesson we learned from preliminary measurement is that we should always avoid baseline 1 when the workload is rate-intensive, and we should avoid baseline 2 when the workload is write-intensive. Therefore, this can avoid the two most expensive Ethereum operations in data feed. We study a dynamic workload-adaptive replication scheme for data feeding. We store a data replica on-chain upon rate-intensive workloads, and we keep data off-chain upon write-intensive workloads. We propose a new data feed system called Graph. This is an overview of Graph. The system has four parties. DO is an off-chain data feed producer, and SP is an off-chain cloud storage provider that stores the data feed. DU is a DF smart contract that reads the data feed from a storage smart contract. We use hybrid storage to store the data feed, and we dynamically replicate the data from off-chain onto the storage smart contract. This diagram shows the detailed design. The most important part is that on DO side, we run a monitor to collect the read request from the blockchain log. And DO also runs a decision maker to decide whether a data feed should be replicated or not. Since the data feeds are primarily stored in SP, which is untrusted, so we run ADLs, which is a Merkle tree, to ensure the data integrity. For more details, please refer to our paper. We propose a novel decision-making algorithm for the decision maker. The algorithm works as follows. We maintain a counter for each data record, and a read will increase the counter by 1. And if the counter reaches to a threshold k, we will replicate, and a write will reset the counter. Let's look at an example. The k is set to be 2. And in the tuple, 0 means the counter's value, and the NR means the decision is not to replicate, and off means there is no on-chain replica. And the first write, we didn't replicate the data feed, and for the first read, we didn't replicate it. And the second read, we will replicate it. And the third and first read will be sold on-chain. And for the second write, we will reset counter, and we don't replicate the data feeds. And the last read, we don't replicate the data feeds. And here's the procedure code of our decision-making algorithm. In the paper, we have proved that the competitiveness of this algorithm is bounded to a constant value, which is 2. For implementation, we built a functional graph prototype, and we implement the on-chain storage smart contract in Solidity. And for the off-chain part, we implemented it in Python and integrate it with LevelDB. We open sourced our code on GitHub. For evaluation, we collected a real-world price feed trees used by stablecoins, and we simulated a MakerDAO DF and replayed the trees into graph and compared the gas cost with the two baselines. The figure shows that at the beginning, graph converges to baseline 1, which is the cheaper one. Then in the latest spikes, graph converges to baseline 2, which is the cheaper one in this phase. In summary, graph saves 11% of gas than baseline 1 and 64% of gas than baseline 2. We also draw mixed YSSB workloads and report the gas cost. We mixed workload A and workload B. The figure shows similar convergence of graph. In total, graph saves 31% of gas than baseline 1 and 45% of gas than baseline 2. We also did extensive evaluation. We collect B3 lay fees in real B3 pack tokens, and the result shows that graph saves 40% of gas than baseline 1, 56% of gas than baseline 2. We also mixed different YSSB workloads, workload A and workload E, workload A and workload F. Similarly, graph saves a lot of gas than those baselines. In conclusion, we proposed a dynamic workload-adaptive approach by mixing on-chain and off-chain data storage. We propose a new data feed system called Graph, which employs a guess-aware online algorithm for replication decision-making. And we implemented Graph and evaluated with real-world data feed trees. And the result shows that Graph can actually save gas than the baselines. Thank you. I'm very happy to answer any questions.